Hi class, this is number 5 and 10.1. Says given the two independent samples below, conduct a hypothesis test for the desired scenario. Assume all populations are approximately normally distributed. So sample 1, and this is I just did a video on number 3, and they had given us the raw data, just actually the actual observations themselves. And we had to take time to find the mean and standard deviation of those from that raw data. In this problem, they give us the statistics from the samples. So they give us the mean of the sample and the standard deviation of the sample. So this is going to be it's going to take one less extra step when we're doing this problem, which is great. So it says, given these samples, conduct a hypothesis test for the desired scenario. And they say, test the claim. Given the alternative hypothesis below, conduct a hypothesis test for alpha equals 0.1. So they already show us that population 1, the null hypothesis is always the two populations are equal. And then the alternative hypothesis is that in this situation, they tell us that population 1 is actually larger than population 2. Now, because in the calculations of the test statistic, what they do is whatever population is lifted here on the left, and they usually always try to keep the 1 on the left and the 2 on the right. But then in the calculation, they do the sample mean minus the sample mean of sample 2. So if true, the sample mean of 1 is larger than 2, then we're going to get a positive answer here. So, which I hope is the case if we're trying to prove that the mean of 1 is mean of the first population is larger than the mean of the second population. I would hope that that's true for at least the samples. So I'm going to expect that this is going to be when I subtract those, it's going to be a right-tailed test. And you can kind of see this from the arrow of the direction that it's pointing in, that it's going to be a right-tailed test. So what I expect to happen is that we're going to subtract these two values and we're going to get a positive number. So it's going to be a positive t statistic over here, like 1.5 or whatever it's going to be, the t statistic is going to be. And then we're going to find the area under the curve. And now when we do that, we're going to be finding the probability of me getting such like 1.5, a difference of that or larger. If the difference is very common, assuming that the two populations don't have assuming that there's no difference between the two populations and there's no difference between the means, if that is a common difference, then we're not going to reject the null hypothesis. But if this difference is very uncommon, which means it's like a really large difference to have, and especially in this particular scenario, then it will have a really low probability, really low p-value probability of happening, and then we'll reject the null hypothesis. So that's what we expect to happen in this problem. And just so you know, when we draw this picture, the value that I'm putting that marks off where the shading begins, that used to be our lower bound, that is the t statistic. That's the net value. And in previous problems in chapter 9, the number along this x-axis that kind of cut off the shading, that was the sample, its sample mean or sample proportion itself, the very sample portion or sample mean. Now I could have translated that to a z-score as well and then found, but I just didn't, because we could just use the actual sample itself. This one's a little bit more different because we actually are looking at the difference between the two sample means. And so I just use the test statistic, which is just, it just is something that kind of helps us find that probability and the curve easier. So this is the p-value, and this is the test statistic. And this, if this is if we look at the alternative hypothesis, it's pointing to the right. So we know that we just shade to the right of this t statistic, and that's what this test is going to look like. So now we just have to enter it into the calculator and do it, get our answers. So it says, given the alternative hypothesis, the test is, so like I said, all you have to do is look at the direction that this, the arrow is pointing from the null alternative hypothesis. So this is pointing to the right. So we're going to say that this is a right tail test, right? If they said does not equal, like we saw in number 3 of this section, then I would say this is a two-tail test, right? Okay, the next part says determine the test statistic. So we're just going to go find the p-value, and then it'll also spit out the test statistic for us. Oh, I was just making up the 1.5 a minute ago, by the way. We're going to actually find what test statistic is now. All right. I mean, like when I was drawing the picture a minute ago, I was like, oh, let's just say our test statistic is 1.5. But that's actually what we're going to calculate. That number needs to go right there. Because I was just making up the 1.5 a minute ago when I was drawing the picture. Okay. So now let's actually calculate it. So I go to, I'm gonna just erase all these other things that I have in here and erase everything here. I guess I'll just erase everything. We'll restart this, okay? So to do this, I just go to stats, and I go to tests, and I just pick out the 2 sample t-test. The t-test is what we do with the mean. We're comparing 2 population means, and because they are taking a sample from 2 different populations, it was a 2 sample t-test. So they tell us this x bar 1 is the mean for population 1, and we actually kind of have to be careful here. It's typical. What I like to do is I like to set up my null alternative hypothesis with the population 1 always on the left-hand side. And that is also the first population that I'm going to put when they say population 1 in the calculator. So I have to stay consistent there. Whatever one I listed in null hypothesis on the left side, then that is also the one I list as number 1 in my calculator. Okay, because you don't want to get those mixed up, because I think your final p-value would probably be right, but your test statistic I think would be like the opposite. So it would be negative when it should be positive and stuff like that, so you don't want to get that wrong because of that. All right, so I'm going to put in my sample 1 population. The x bar here is 382. So 382. Then they want the standard deviation of the first population, so it's 155. Then they want the sample size of the first population, the N1, which is 852. It's a big sample size. And then they want the x, the mean, the mean from the second one, which is 384. Now we're going to the second population. And then the mean from the, the standard deviation from the second one is 168. And then the standard the number in 2 is 826. And they have this particular program just gives us all the p-values for any, whether left, right, or two-tailed, or not equal. So we have to look at our situation. And we have, in our alternative hypothesis, we have the alligator's mouth pointing to the left. So that we need to, that's what we need to find here. So that is right here, is the alligator's mouth pointing to the left. So this is the p-value that we want. There we go, 0.59. And so let's just double check our answer here. So, oh, and then the t-statistic is something they automatically give us, is the 0.025325. So that is correct. And the p-value is correct. Now, this is a problem that just kind of irks me a little bit. They were like, we're trying to prove that the mean of population 1 was larger than the mean of population 2, like the actual mean of the entire population, not just like of the mean of the sample, right? But then they're like, here's my evidence to support the fact that I think population 1 has a bigger mean. They bring evidence to the table, and not even the mean in their sample is larger than the mean in, the mean from sample population 1 isn't even bigger than the sample mean of population 2. So this is not evidence to show our case, which frustrates me as a professor, because like, I'm like, if you guys are trying to prove this is right, and this is not even evidence to say that, to prove your case, you know, so that's disturbing to me. I don't like this problem the way it's set up. So I apologize about that. In reality, I think if this was truly a real life problem, like I said, this would be you would have gotten a test statistic. If this mean were larger than that mean, you would have got a test statistic over here to the right, which would be a positive t value here, t statistic here, and you would have had a smaller p-value. But and your picture would kind of look more like this. But in our situation, the value is actually right here, this negative 0.25, and our p-value is actually this. Maybe that makes sense why it's larger than 0.5. So the test statistic, that is what we label along the x-axis and becomes like our lower bound or cutoff of that shaded region. And then the actual area of the shaded region, that is the p-value probability of getting a sample like that or larger. And it's very common to occur. If these two populations are, the mean of those two populations are the same, then this is a very common sample to get. And in fact, it happens 60% of the time, right? 59% or 60% of the time. So this is not evidence against the null hypothesis. And we would next be asked, is the p-value less than alpha? Well, alpha up here alpha is 0.1, and so p-value is 0.5. So the p-value is not less than alpha. We do not reject the null hypothesis. So we would say we fail to reject the null hypothesis here. And that's the end of our problem. And I don't think do they make us, no, they don't make us like actually say, but because we fail to reject the null hypothesis, it means we do not reject the null hypothesis. That means we do not think that there's sufficient evidence to prove the alternative hypothesis, that is the mean of population 1 is larger than the mean of population 2. Right. So I apologize. I feel like this problem is a little bit wacky because they're like, we think mean of population 1 is bigger than mean of population 2, but we bring a sample to prove it, and our sample isn't even evidence to support it at all, because the mean of sample 1 is not bigger than the mean of sample 2. Like, so it's just kind of a silly problem that they made here. I apologize, but at least we can do all the steps and there's nothing wrong. They're not giving us the wrong answers. It's just kind of a silly thing to do. But anyways, I hope you guys I hope you found this very understandable. Please let me know if you have questions. Bye.